Somewhere out there, past Pluto, past the last outpost of anything we'd call home, a machine older than most of the engineers who monitor it is still whispering back to Earth. Today is July 22nd, 2026, and right now, at this exact moment, a signal is crawling through the dark toward a spacecraft so far away that light itself, the fastest thing in existence, takes nearly 23.5 hours to reach it. Not 23.5 minutes. Hours. That spacecraft is Voyager 1. It launched in 1977. Disco was on the radio. Nobody had a cell phone. The idea of the internet was a rumor in a handful of research labs. And yet this single piece of 1970s hardware, with less computing power than a modern car key, has outlived its own mission by nearly 5 decades. And it is still, right now, sending us data from a place no human-made object has ever been. Confirmed fact. According to NASA, Voyager 1 is currently more than 25 billion kilometers from Earth, roughly 15.8 billion miles, making it the most distant human-made object in existence. Confirmed. Fact. On November 15th, 2026, NASA calculates that Voyager 1 will cross a distance of 25.9 billion kilometers from Earth. At that point, for the very first time in human history, a signal traveling at the speed of light will take a full 24 hours, one entire light day, to reach a machine we built. Sit with that for a second. Right now, in July 2026, if you wanted to send Voyager 1 a message and get a reply, you'd be waiting the better part of 2 days. By this November, you'll be waiting 2 full days minimum just for your words to arrive, and another full day for the answer to come back. That's not science fiction. That's a real countdown happening on NASA's own tracking systems today. But distance was never really the story of Voyager 1. Distance is just the stage. The real story is what Voyager 1 has been finding out there in a region of space so alien, so unmapped, that scientists genuinely did not know what to expect when the probe first arrived. Here's what almost nobody remembers. Voyager 1 wasn't built to do any of this. It was designed for a 5-year tour of Jupiter and Saturn. It photographed erupting volcanoes on Jupiter's moon Io. It uncovered previously hidden rings around Jupiter and new moons that no telescope on Earth had ever detected. It was supposed to take its pictures, beam them home, and quietly fade into history as a job well done. Instead, something in mission control decided this little machine deserved a second act, and a third, and, as it turns out, a 5th decade. In 2012, Voyager 1 did something no spacecraft had ever done. It crossed the heliopause, the outer edge of the enormous bubble of charged particles that our sun blows out into space, called the heliosphere. Think of the heliosphere as an invisible force field generated by the sun itself, stretching billions of kilometers in every direction, holding back the raw, hostile radiation of interstellar space. Cross that boundary, and you leave the sun's protection behind entirely. You are, for the first time in human history, in true interstellar space, the space between stars. Confirmed fact. Voyager 1 and its twin, Voyager 2, remain the only spacecraft ever to operate outside the heliosphere, according to NASA. That alone would have been enough to make Voyager 1 immortal in the history books. But it's what happened after that crossing, what Voyager 1 has been quietly measuring in the years since, and especially in the most recent data released this year. That has scientists rethinking something fundamental. Not about Voyager, about us, about the shield that has protected every human being who has ever lived. Because here's the uncomfortable question that recent research is now forcing astrophysicists to confront. What if that shield isn't as strong as we thought? We are. Not talking about danger to Earth tomorrow. Let's be clear about that immediately, because this is exactly the kind of story that gets warped into panic online. Nothing here threatens anyone on this planet next week, next year, or in our lifetimes. This is deep science, slow-moving, measured in decades and centuries. But the implications for how we understand our solar system's place in the galaxy and how fragile that placement might be are enormous. Voyager 1 is dying. That's not dramatic language, it's simply true, and NASA says so openly. It runs on radioisotope thermoelectric generators, essentially chunks of decaying plutonium converting heat into electricity. That fuel source has been quietly weakening every single year since launch. Confirmed fact, Voyager 1 and Voyager 2 lose an estimated 4 watts of electrical power every year, according to NASA engineers. To survive, mission control has had to make brutal choices. One by one, instruments have gone dark, not because they broke, but because engineers deliberately switched them off to conserve the last drops of power, hoping to keep the spacecraft's heaters running just a little longer against the deep cold of interstellar space. Confirmed fact. On April 17, 2026, NASA engineers at the Jet Propulsion Laboratory shut down Voyager 1's low-energy charged particles instrument an instrument that had been running almost continuously since 1977 to save power. This is a spacecraft in its final chapter, fighting for every additional data point, every additional year, every additional secret it can pull from a region of space humanity may not visit again for generations. And in that final chapter, in the last flickers of its long life, Voyager 1 may have stumbled onto the most important discovery of its entire 5-decade career. A crack, a genuine, measurable weakness in the wall that separates our solar system from the raw universe beyond. To understand what that crack actually is, and why scientists are so unsettled by it, we need to go back to the boundary itself, the heliopause, and take a much closer look at what's actually happening there. That's next. To understand what Voyager 1 may have found, you first need to understand what it's actually looking at, because most people have never heard of the structure that protects our entire solar system, let alone that it might have a weakness. Picture the sun not just as a source of light and heat, but as an engine constantly firing out a stream of charged particles in every direction. Scientists call this the solar wind. It races outward at hundreds of kilometers per second, and as it travels, it inflates an enormous bubble around our entire solar system. The sun, Earth, every planet, every moon, every asteroid, all wrapped inside this bubble like a snow globe. That bubble is the heliosphere. For billions of years, the heliosphere has acted as a shield, deflecting a large portion of the galactic cosmic radiation that constantly bombards the galaxy. High-energy particles blasted out by exploding stars and other violent cosmic events, light years away. Without that shield, more of that radiation would reach the inner solar system, including Earth. At the outer edge of this bubble is a boundary called the heliopause, the precise line where the pressure of the sun's solar wind finally gives out, and the pressure of the interstellar medium, the thin soup of gas, dust, and magnetic fields that exists between stars, takes over. Confirmed fact. Voyager 1 crossed the heliopause in 2012, becoming the first spacecraft to enter interstellar space, as confirmed by NASA and JPL. Crossing that line, Voyager 1's instruments detected something dramatic: the density of particles. Outside, the heliosphere jumped roughly 40 times higher than what the spacecraft measured just inside it. That single number confirmed beyond a doubt that Voyager had truly left the protective bubble behind. But here's where the story gets strange, and where the science becomes genuinely uncertain, in a way that has honestly kept researchers arguing for over a decade. When Voyager 1 measured the direction of the magnetic field in interstellar space, the numbers didn't match what scientists expected based on other spacecraft and telescopes. The discrepancy was significant, more than 40 degrees off from predictions. For years, this was treated as a full-blown mystery. Was Voyager 1 even really in interstellar space? Was the instrument malfunctioning? Was our whole model of the heliosphere wrong? Theory, later. Supported by evidence, a team led by physicist Nathan Schwadron of the University of New Hampshire proposed that the discrepancy wasn't an error at all. It was real data revealing something new. Their research suggested that just outside the heliopause, the interstellar magnetic field gets bent and dragged around the heliosphere, the way wind currents wrap around a mountain or an elastic band stretched around a beach ball. Voyager 1, they argued, was flying through this distorted, muddied transitional region, not yet in pristine, undisturbed interstellar space. Their models predicted that by around 2025, if Voyager 1 continued its outward journey, the spacecraft's magnetic field readings should gradually rotate and finally align with independent measurements from other observatories, signaling true entry into clean, unperturbed interstellar territory. So, did that happen? This is where the most recent, most current data becomes genuinely fascinating. Confirmed fact. A study published in the Astrophysical Journal in May 2026, using Voyager 1 data collected from 2020 through mid-2025, found that the magnetic field environment around the spacecraft is still behaving in unexpected ways. Researchers observed a distinct region they call the magnetic hump, where the field strength jumped and then, unlike previous disturbances, never fully relaxed back down. Instead, it settled into a sustained, elevated strength, hovering steadily between roughly 0.45 and 0.53 nanotesla. In plain language, something out there pushed on the magnetic field, and unlike earlier disturbances that came and went, this one left a lasting mark. The field didn't bounce back to normal. It found a new, higher normal. It stayed there. Confirmed fact, per the same study, the research also tracked turbulence in the magnetic field, essentially how chaotic and unpredictable the fluctuations are. Overall, that turbulence has been trending downward since a major pressure event researchers call PF2, the second pressure front. But it hasn't disappeared. Certain components of the field showed unexpected spikes of instability in 2023 and again in 2024 before settling down once more in early 2025. The scientists' own conclusion, stated directly in their published paper, is worth repeating precisely because it resists hype. Voyager 1 has not yet transitioned into a pristine interstellar medium, completely free of the sun's influence. It remains in a perturbed, very local interstellar medium environment, one still characterized by weakening but persistent intermittent turbulence. That's the confirmed science, careful, measured, full of appropriate scientific hedging. Now here's the part that has captured public attention and fueled the weakness framing you may have seen in headlines. Separate reporting on Voyager's more recent magnetic field readings, drawing on the spacecraft's ongoing observations, described something that sounds almost paradoxical. Instead of interstellar space feeling weaker and thinner the farther Voyager traveled, its magnetic field lines appeared stronger and more ordered than models had predicted. Theory. Emerging interpretation. Some researchers have suggested this could mean the magnetic pressure of interstellar space, the pressure pushing back against our sun's heliosphere from the outside, may be greater than previously believed. If that interpretation holds up under further study, it would suggest our solar system's shield isn't simply expanding into empty, passive space. It's locked in an active, ongoing tug-of-war with genuine pressure from the galaxy beyond, a tension that shapes and warps the boundary like a balloon under pressure, in the words of some scientists studying this frontier. This is the closest thing to a real weakness in this story. Not a hole, not a breach, but growing evidence that the wall around our solar system is a dynamic, contested, physically stressed structure. Not a static, impenetrable fortress the way it's often imagined. And Voyager 1, almost by accident, in the final years of its dying transmission power, may be the only witness we have to that tension, measured directly from inside the boundary itself. But why does any of this actually matter to us here, safely inside the bubble? What does a stressed, contested heliosphere mean for Earth, for the future of exploration, and for the next spacecraft that will eventually have to follow where Voyager led? That's where we go next. It's tempting to hear all of this and ask, so what? It's a magnetic field, billions of kilometers away, measured by a machine that can barely keep its heaters on. Why should anyone on Earth care? Here's why. The heliosphere isn't just an abstract bubble of interest to physicists. It is, functionally, one of the reasons complex life on Earth has had a relatively stable, protected environment to evolve in for billions of years. It filters out a significant portion of galactic cosmic rays, extremely high-energy particles that come from exploding stars and other violent events across the galaxy. Too much unfiltered cosmic radiation reaching a planet's surface can damage biological systems, and even DNA over long timescales, and it can interfere with electronics in human spaceflight. Confirmed fact, Earth's atmosphere and magnetic field provide additional layers of protection beyond the heliosphere, but the heliosphere itself is the first, outermost line of defense for the entire solar system. So when scientists find evidence that the boundary of this shield is more turbulent, more actively pressured, and behaving differently than older models predicted, it's not just an academic curiosity. It reshapes our understanding of how protected we actually are, and how that protection might change over the extremely long timescales involved in stellar and galactic evolution. To be direct and responsible about this, nothing in the current data suggests any near-term risk to Earth. The changes being measured are happening across years and decades in a region of space so far away it takes light nearly a full day to cross it. This is not a countdown to catastrophe. It's a correction to our understanding. And in science, corrections like this are often the most valuable discoveries of all, because they reveal that reality is more intricate than our models assumed. There's also a second, more immediate reason this matters. It's reshaping how we think about human exploration beyond the solar system. Confirmed fact. According to NASA, at their current speed of roughly 35,000 miles per hour, it would take the Voyager probes about 40,000 years to reach the region considered the true, indistinct edge of the sun's gravitational and physical influence, a boundary far beyond even interstellar space, sometimes associated with the theoretical Oort cloud region. 40,000 years. Let that number sink in. Voyager 1, the fastest, farthest flung object humanity has ever built, moving at roughly 10 times the speed of a rifle bullet, would still need 40 millennia just to reach the outer edge of our own sun's zone of influence. That is the staggering scale we are actually talking about when we talk about leaving the solar system. Interstellar space, where Voyager 1 already is just the very beginning of that outer frontier, not the end of it. This is part of why the data Voyager 1 is sending back right now in 2026 is considered irreplaceable. There is no other spacecraft anywhere near this region of space. none currently under construction, will get anywhere close for decades, possibly longer. Everything we learn about this specific transitional zone between our solar system and the wider galaxy is, for the foreseeable future, coming from one aging, failing machine and its slowly dimming twin, Voyager 2. Which brings us to the second major story unfolding in 2026, a story just as dramatic as the science itself, the fight to keep Voyager 1 alive, long enough to keep collecting this data at all. Confirmed fact. NASA engineers have nicknamed their latest attempt to extend the Voyager missions the Big Bang, a bold engineering maneuver designed to reroute and rebalance the spacecraft's dwindling power supply. If successful on Voyager 2, engineers plan to attempt the same fix on Voyager 1 in July 2026, this month. Think about what that actually means. Engineers, working with technology and documentation from the 1970s, using backup systems that haven't been touched in decades, are essentially performing high stakes surgery on a patient 25 billion kilometers away, with a communication delay of nearly a full day between every single command sent and every confirmation received. There's no room for a quick fix, no chance to react in real time if something goes wrong. Every decision has to be exactly right, because the round-trip conversation with the spacecraft, command sent, response received, can take nearly 2 full days. If the maneuver works, it could allow the low-energy charged particles instrument, the very instrument that was switched off in April 2026 to save power, to be reactivated. That instrument, according to its principal investigator, Matt Hill of Johns Hopkins Applied Physics Laboratory, was directly responsible for helping scientists first detect the properties of cosmic rays and solar particles, and for sensing the very transition when Voyager crossed from our solar system into interstellar space in the first place. Losing it permanently would mean losing one of Voyager's most historically important senses. This is the real tension driving the story in 2026. An irreplaceable scientific instrument, orbiting through one of the most consequential unexplored regions in the entire solar system, racing against a countdown clock powered by decaying plutonium, while at the very same time, that instrument may be sitting on evidence of a genuine measurable weak point in the shield that has quietly protected human civilization for its entire existence. 2 clocks are ticking at once. One counts down Voyager 1's power. The other counts patiently the shifting pressure of the galaxy against our solar system's edge. And for a brief window, right now in 2026, humanity has a single working witness to both. So where does this leave us? What happens when Voyager 1 finally does go silent for good? And what does its discovery actually mean for how we should think about our place in the universe? Let's bring it all together. Let's be completely honest about where the science actually stands today, July 22nd, 2026, because that honesty is what makes this story worth telling in the first place. Voyager 1 has not discovered a hole in the universe. It has not found proof that Earth is in danger. It has not confirmed some hidden flaw that threatens our solar system's survival. Anyone telling you that is not describing real science, they're describing a headline stretched past what the evidence supports. What Voyager 1 has done is quietly, patiently, over more than a decade of operating in a region of space no other instrument has ever touched, gathered enough data to force scientists to revise their assumptions about the boundary between our solar system and the galaxy beyond. That boundary, the heliopause, is not the clean, static wall many people imagine. It is contested territory, a place where the outward push of our sun's solar wind and the inward pressure of the interstellar magnetic field are locked in a slow, ongoing tug-of-war, leaving behind magnetic humps that don't fully relax, turbulence that flares and calms in unpredictable cycles, and field strengths that behave differently than pre-Voyager models ever predicted. Confirmed fact, restated carefully from the May 2026 study. As of the most recent published analysis, Voyager 1 remains inside a disturbed, very local, interstellar environment, still shaped by the sun's influence, not yet within a pristine, undisturbed region of true interstellar space. The open question, honestly labeled as unresolved. Whether the interstellar magnetic pressure pushing back against our heliosphere is truly stronger than earlier models assumed, the closest thing to a real weakness in our shield's expected performance, remains an active area of ongoing research, not a settled fact. It is a compelling, evidence-supported hypothesis. It is not yet scientific consensus. That distinction matters. Real science almost never arrives as a single, clean, headline-ready answer. It arrives in exactly this messy, careful, argued-over way, one measurement at a time, one paper at a time, one cautious sentence at a time, refined over years by researchers who are far more interested in being right than in being dramatic. And that's precisely what makes Voyager 1's role in all of this so remarkable. This isn't a billion-dollar flagship mission built with today's cutting-edge sensors. It's a spacecraft designed with 1970s technology, running on a power source that loses a little more strength every single year. Its team forced to switch off working instruments one by one just to keep it breathing a little longer. And even now, weakened, half-blind compared to its original capabilities, its signal, taking nearly a full day to reach us, it may still be the single most important source of first-hand data we have about the true edge of our solar system. Confirmed fact. NASA and mission engineers attempted the power-saving maneuver nicknamed the Big Bang on Voyager 2 first, with the intention of applying the same fix to Voyager 1 this month, July 2026, if successful, an active effort to restore power to instruments like the low-energy charged particles experiment. Whether that maneuver succeeds is, as of today, still part of an unfolding story. Voyager's entire mission has always been a story of borrowed time, of scientists squeezing every last piece of value from a machine that, by any reasonable engineering standard, should have gone silent decades ago. And here's the piece of this that deserves to be said plainly, without exaggeration, because it doesn't need exaggeration to be extraordinary. Within the next few years, quite possibly within the next decade, Voyager 1 will finally run out of power completely. Its heaters will fail. Its transmitter will fall silent. It will become, forever, humanity's most distant, most silent monument, still moving outward at over 35,000 miles per hour, carrying its golden record of Earth's sounds and images into the dark, but no longer able to tell us anything about what it's flying through. Confirmed fact, NASA has stated that even after Voyager 1 stops transmitting, the spacecraft itself will continue moving outward indefinitely, eventually, over tens of thousands of years, passing beyond the outer edge of the sun's sphere of influence, entirely. When that silence finally comes, everything we know about this specific region of interstellar space, the magnetic humps, the turbulence, the tug-of-war at the heliopause, the possibility that our shield faces more resistance from the galaxy than we once assumed, will be, for a long time, all we have. No mission currently exists that will replace Voyager 1's vantage point anytime soon. Whatever it manages to send us before it goes quiet is very likely the last word on this frontier for a generation, possibly longer. That is the real weight of this story, not a sudden universe-shaking discovery. Something quieter and, in its own way, more human. An aging machine, built by people who could never have imagined the internet or smartphones, still doing its job at the very edge of what we understand, patiently sending home evidence that the shield protecting every person who has ever lived is not as simple, not as static, and not as impenetrable as we assumed. Just contested, just dynamic, just real. We built something in 1977 that is still teaching us in 2026 that the universe doesn't offer clean, easy walls of protection. It offers pressure, tension, and constant negotiation at every boundary, all the way out to the edge of everything we know. And somewhere out there right now, 25 billion kilometers away, moving at 10 times the speed of a bullet, that little machine is still listening, still speaking, still teaching us, one faint signal at a time, just how much we still don't know about the wall between us and the rest of the galaxy.